Hey everybody, how's it going? Welcome back to Geocentric Kingdom. Been a while. In this episode what we're going to do is take a look at some anti-flat earth pages, take a look at what they have to say against flat earth and just simply debunk them, and then at the end of the video I'm going to go into what I consider the three most simple flat earth proofs that if anybody has any doubt or any questions, there are these really easy facts that you can bring up that are pretty controversial when it comes to trying to convince someone you believe that you live on a globe. Instead, they actually support the idea of a flat earth. So what I'm going to do is I'm going to Google search most simple flat earth proof. Alright, now what I want you to see here is just take a look. I'm looking for flat earth proof, and what we see are search results that prove the earth is not flat. 10 easy ways you can tell the earth is not flat. Prove flat earthers our planet is round. You know, how to argue with flat earthers, prove the earth is round. So kind of interesting there. We're looking for flat earth proof and all these anti-flat earth searches come up. Bit of a fail on Google's end there, but let's just click on the first one and see where it takes us. You don't need to build a rocket to prove the earth isn't flat. Here's the simple science. Alright, let's skip ahead here. Let's see, one of the best documented methods to determining the Earth's roundness was first performed to our knowledge by the ancient Greeks. Oh yes, the ancient Greeks are so wise. This was achieved by comparing the shadows of sticks in different locations. This is real science here. This is like, you know, this was the original laboratory. This was achieved by comparing, when the sun was directly overhead in one place, the stick cast no shadow. Stick directly beneath the sun. At the same time, in a city around 500 miles north, the stick there did cast a shadow. Wow. Okay, so if the earth were flat, then both sticks should show the same shadow, or lack thereof, because they would be positioned at the same angle towards the sun. Take a look at this. Let's look at that again. If the earth were flat, then both sticks would either show the same shadow or no shadow at all, because they would be positioned at the same angle towards the sun. So what do we got here? They're saying, actually I won't even make a ball, we'll just make a part of the curved earth here. This is part of the curved earth. If you got one stick, you know, over here and one stick over here, and you got the sun up here above this stick, that's not a circle. You got the sun here, the sun rays are coming down on this shadow, or on this stick here, and the shadow is barely anything, right? Whereas the sun rays are hitting this stick here, and I don't know why that turned yellow, but the shadow would be cast like this, you know, pretty long, considering the angle, but it would be a shadow. And now they're saying, scrap all this, if you had a flat earth, and you had the sun, if you tried to perform the same experiment with the stick underneath and the stick over here, they're saying that this shadow would be either like this, and this shadow would be the same, or this shadow would be like this, and this shadow would be like this. Based on what they say here. If the earth were flat, then both sticks should show the same shadow, or lack of, because they would be positioned at the same angle toward the sun. Why would they be positioned at the same angle toward the sun? Are they trying to argue that I need to put my sticks like this? One would be toward the sun, and the other one would be toward the sun, and that way this shadow is directly beneath this stick, and then this shadow is directly beneath this stick. Why do you have to do that on a flat earth? So this one's pretty stupid. I'm not even gonna try and say I debunked it. It's just there's nothing to debunk. All right. Another piece of evidence for the globe is the difference between night skies in the northern and southern hemispheres. The view is completely different because the earth beneath you is pointing in a different direction. If the earth were flat, then the view should be the same. Now this claim is making another assumption, and that is, if the Earth were flat, the view should be the same. According to the flat Earth theory, that's not true. According to the flat Earth theory, you've got the level Earth that we live on, and first of all, we don't have hemispheres. We have the firmament, the dome firmament, which is the solid physical sky above the Earth, okay, which is why rainbows are shaped like an arc, all right? And I'm not even going to get into how this creates a lens effect with the waters above and the waters below. We're just going to focus on how the air inside of our environment, this world that we live in, actually acts as a lens. And it refracts light. So in the same way that you can look for refraction in a cup of water, the water is more dense than the air around it, and so the image of the straw actually appears lower than reality. If, for example, the water were less dense than air, first of all, it would want to float up out of the cup. So, you'd flip the cup upside down, you'd stick the straw in from underneath, and then the image of the straw would actually be above where it is here. It would be higher, right? Or if you just filled this thing up and with something lighter than air and then you sealed it off, this refracted image would actually be on the other side of the actual straw that we see. And so what happens in our world is if you're trying to view something, and now this is going to be totally out of scale, but if you're trying to view a tree here, and you're on this part of the flat Earth, and you're looking across, say, a body of water, the light from the top of the tree, as it, ordinarily you'd think, yeah, okay, on a flat Earth, the light should travel all the way across, and you should be able to see the entire flat Earth from a high enough point. But the bottom line is, you got the most dense air right on the level of the Earth, on the ground, and then you got less dense air the higher you go up. So no matter what, you're in some form of refracted light because you're in a medium, and it's got some density to it, and so the light plays funny in it. You wouldn't be no one would make fun of you for assuming that light should just shoot across the flat Earth like there's no big deal. But in reality, the top of this tree, as the light bounces off, say, the sun, the light from the sun bounces off the tree and then goes to reach you, it actually is refracted down. The image of the tree is refracted down, and so you can only actually see the top of the tree from so far away. Now this principle also works when you apply it to, say, birds flying overhead. If you're standing here, right, and a bird flies overhead, let's just call this a bird, all right? Let's see. If the bird were directly ahead of you, on top of you, you would be looking straight up. And as the bird flies away, you are looking down, 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 closer and closer to the horizon, right? So first you were looking directly up, and then as the bird flies away, you're looking closer and closer toward the horizon. And eventually there comes a point where the bird, I have to lower it because, this isn't to scale. There comes a point where the bird gets so far away, it's basically on the horizon. Or if it's a plane or a helicopter, whatever, it gets to the point where the plane will actually look like it's going down toward the horizon. But that's not true. You know that the altitude is still the same. But the closer something gets to the horizon, the lower it appears to be. And this lens effect also, it makes things appear lower than they really are in reality. So the same principle, if you had the North Star above you, I've got a great example I can pull up and I'll show you. Somebody did a wonderful animation. I think it was
how the stars are, and let's say the stars actually spread out for hundreds, thousands of miles, let's say, and let's say we can't see them all. We can only see the dome of our perspective vision, which is about a 12,000 mile diameter circle or 6,000 mile radius. That's all the stars we can see. And the stars lower to the horizon at the edge of that circle, of a 12,000 diameter circle. So as you move, this dome of stars moves with you, or your dome of vision, I call it. Anyway, let's check it out. Well, just like, let's say you're standing at the North Pole, right? And the stars rotate. You have Polaris overhead, and the stars are rotating around you counterclockwise. As you move south, Polaris starts to lower in the northern sky, and the stars start to tip. It's almost, I like to think of it as like a salad bowl, right? And so the salad bowl has the bottom is up, that's where Polaris is, and the rim of the bowl is on the ground. That's also where the sun would go around. So as you head south, the salad bowl starts to tip onto its side, and so that, let's say you travel 3,000 miles south of the North Pole, everything would be rising in the northeast, sweeping out over the southern sky, and setting in the northwest, like this, right? And if you go all the way to the equator, Polaris would now be sitting on your northern horizon. The salad bowl would be completely tipped on its side, and half of it would be below the horizon. And now all the stars would be coming up east to west. And so the sun would also rise east to west.
The third point is you can observe the planets as well. They all rotate, and watching over the course of a few days gives a clear picture that they are spherical rather than flat. The chance that most of the planets are spherical but Earth is flat seems very unlikely. So again, this is you can't come at one theory. Like you can't this isn't scientific. You cannot come at one theory assuming all of the biases of another theory. The flat Earth theory is completely separate from the globe Earth theory. Or if you don't want to call it a theory, it's a model. If you subscribe to and believe in the globe Earth, you can't investigate the flat Earth assuming all of globe Earth is true. You need to, if for science's sake, you need to put globe Earth beliefs in suspension and try to actually delve into flat Earth beliefs and see why people believe what they believe about the flat Earth. If flat Earth is true, then all the things you would assume about globe Earth don't count for now while you're investigating. So this guy says you can observe the planets as well. They all rotate, watching over the course of a few days. They're spherical rather than flat. No flat earther will argue with you over that. You know, on the flat Earth, you know what we can do is we look up at the firmament, we look up at the sky just like any globe earther, and we see things on the firmament. The globe Earth says they're in space. We say, yeah, they're in the firmament. They're actually in the waters above the firmament, according to the Bible, according to Genesis, right? If there's spherical objects up above the firmament, who cares? That doesn't mean Earth has to be spherical as well. Not in the flat Earth model. The flat Earth model assumes that the Earth is flat and that there's bodies, celestial bodies, up in the water. So no problem there. You can't just assume. You can't input your globe model biases into another model's, you know. Now this article also gets into fake science, you know, making fun of flat Earth experiments. We're not really going to get into that. We're going to look at another, yeah, okay, here we go. 10 easy ways to see that the Earth is not flat. We're just going to pick apart each of these arguments because they're not good, all right? Let's see. All right, now for this next argument, they say the moon proves that the Earth is a ball, and it simply comes down in this example to the lunar eclipse. And I'm not really going to dive into it. You know what the lunar eclipse states is that the moon floats around the Earth, and that the way that the sun hits the Earth and casts a shadow on the moon, this proves that everything is a ball. Everybody's gone crazy for balls, all right? But this has already been brought into question, let's say, by a great video here by Potter's Clay. All right, he's a great Christian Flat Earth YouTube channel. You should check him out. In this video, very plainly, he compares the size of the moon's shadow, so a solar eclipse, the moon's shadow on the Earth, like this. If the moon, you know, is 2,159 miles wide, you know, in diameter, it casts a shadow only 70 miles wide on the Earth. If you do some simple math, you know, so far as an actual lunar eclipse goes, then doesn't the math alone tell us that if the same light was cast on an object roughly 4 times the size of the first object, which is the Earth compared to the moon, that the shadow would be only 4 times the size as well? So this is just taking the solar eclipse, doing the math with the size of the shadow on the Earth, and then reversing it, because whether the moon's in front of whether the Earth is in front of the moon or whether the moon's in front of the Earth, they're the same distance apart, and so the same math and the same physics should apply because the distance is the same. All right, so as you work through, basically we should be seeing a shadow pretty small on the moon. If an object the size of the moon casts a shadow on the Earth only 70 miles wide, then an object the size of the Earth should only cast a shadow on the moon 4 times as wide. But what we have instead is a massive, massive shadow on the moon. And so what I can even do is I can take a screenshot here, and I can open up Paint again. And what we're going to do is take this image and try and figure out how big the shadow actually is. Let's make it so we can see it. That puts the curvature at about, I mean, it's not perfect, but according to the math, the size of the shadow on the moon of the Earth, the shadow of the Earth on the moon, should only be 256 miles wide, according to the math, according to Potter's Clay. And I believe that this is accurate, because if the size of the moon's shadow on the Earth is only 70 miles wide, you know, the shadow's shrinking down from the size of the moon. The shadow of the Earth should also be shrinking down proportionately, and so we should see a shadow 256 miles wide. If the moon is 159 miles wide, the shadow should be small on the moon. But clearly the shadow is huge. This is like the full range of the shadow, approximately. And so, going back to what I said before, if you want to look into the flat Earth model, you can't bring in the globe Earth biases and assume that globe Earth ideas are true and that they will apply to the flat Earth idea. The flat Earth idea, the flat Earth concept, the flat Earth model, theory, whatever you want to call it, comes with its own package of explanations for what we see. And according to the flat Earth model, the sun and the moon, as far as Genesis tells us, the sun and the moon and all the stars are actually up above the firmament, and there are, according to the theory, not according to the Bible, but according to the theory, there are other celestial bodies up there, or maybe not. There's just, the Bible says that the moon itself is a light source, and I think you can tell clearly from looking at, the math and then comparing the actual size of the shadow on the moon, something's not quite right here. So people have reason to believe that in the flat Earth model, maybe there's actually lenses or other bodies, or parts of the moon getting shut down at a time through the eclipse. Clearly this is not the Earth's shadow. Alright, let's move forward. Look at the next one. Ships in the horizon. This one I already kind of debunked by looking at perspective. If you don't believe it, that's your problem. You have to leave globe Earth biases behind. Except that what the flat Earth model says is that as a ship sails away, there's refraction in the air, especially over the ocean, because the air above the ocean is especially dense because water is evaporating constantly. And so as you're looking through the air, the image of the ship is going to actually bend down, so you're going to see less and less of the ship as it gets further and further away, because you're looking through more and more medium. Can you see forever? We can assume that this bottom of the part of the ocean here that this guy's scuba diving, or maybe it's a lake. I bet it's the ocean. You could assume this is probably pretty flat, right? But you can't see forever because the water's too thick. There's too much dust. There's particles in the water. The same applies to above the water. The air has matter in it, and you can't see forever. That's just the law. If you wanna argue, well, I should be able to see forever on the flat Earth, that's a childish, unstudied argument. Moving forward, varying star constellations. Aristotle said, well, I can see different stars from different parts of the world, and I already went over this one before in the last argument. You should be able to see everything from the flat Earth. Nope, that's not true. You're bringing globe biases into flat Earth theology, or flat Earth, the flat Earth model. Now we have the shadows and the sticks. So I guess this is what they meant. Maybe I was wrong in the first argument. They're saying the sunlight should be coming down and hitting the sticks from the same angle. The funny thing is, they put these sticks like, yeah, if these sticks were like 10 feet apart, you'd have the same shadow. Same with on the globe. But they go ahead and say, see, look, these sticks on the globe, they put them far enough away, to scale. If this is actually how much curvature is between them, these things are like hundreds of miles away. The same effect of different shadow lengths would happen on the flat Earth if you put the sticks hundreds of miles away. So don't get fooled by a really bad argument supporting the globe. This is an image of sticks really close together. If you stuck them far enough away, what you have on the flat Earth is, forget deleting stuff, I'm just gonna show you. You'd have a stick over here, oops, it's gotta be black. You'd have a stick over here and a stick over here, and if this is the sun, the light cast over here would cast a shadow like that, and the light cast from here would cast a shadow like that. That's the equivalent of what they're saying is happening here. That's how far away it has to be. So it's a bad argument. It doesn't apply. I don't know what this is. Seeing farther from higher. This is actually one of the flat Earth proofs that I wanted to use. So maybe I'll just, yeah. So you can already tell what's going on here. You're higher up, you can see over the curve, right? That's what they say. But you know what? Let's just get started. Sure, I'm going to dig into the flat Earth easy proofs now, and I guess we'll just start with this argument: seeing farther from higher. According to the flat Earth theory, in this image, you can see this tree from here, and if you go higher, you can see the same tree. Great. That doesn't prove anything. You know what they're missing out is what's beyond the tree. All right, so this is biased. You're standing on the round Earth. You can only see so far. Your line of sight here just shaves over the horizon there, and you can't see the tree. But if you climb up higher, then you can see over the horizon. You can still see the tree. Now look what they're missing though. Something you should take home from this is that if you go higher on a globe, actually back up a bit. Basically, the globe model says that the horizon that you see when you look out, and there's about 3 miles of distance between you and the edge of the ocean there, and that horizon is supposedly the curve of the Earth, and that's what's being argued in this cartoon. So this guy, Mr. Red, he can only see to the horizon, and then he's seeing out into space everything above the horizon. If you gain some altitude here, like Mr. Green, you look down over the horizon, and then you can see the tree. But notice he's looking further down. He's looking further down over the horizon because on the ground, on the Earth, everything on the other side of the curve of the horizon should be lower than the horizon. Listen to what I'm saying. When you look at the horizon, everything behind the horizon that you can't see should be lower down. I'm going to take my cursor here. I'm going to bring it down. Then I'm going to bring it to the left, and it lines up with the tree. If I'm at the horizon, if I bring it straight left, everything behind this horizon line that you can see, that Mr. Red can see, everything behind it is down. It's lower. So in order to see it, you need to climb up, and you're looking down on the horizon, then you can see the tree. What does it really look like in real life, though? The higher you get, this is a good image. Whether you're at sea level, the horizon is this high. So if the tree is down below the horizon here, as you ascend into a plane, you should be looking down on the horizon, and then you'd see the tree. What actually happens is the horizon stays in the same place, and more of the plane of the Earth is revealed. And even if you're way up high, super high altitude, the horizon is still level, and you're not looking further down on a curve. Like the horizon should be like, look at what his horizon looks like now. As he looks at the horizon's lower. This point where he sees the horizon is lower than this point where he sees the horizon. This is an anti-globe argument. Do I have to draw it for you? Where this guy sees the horizon, his horizon is like right here. That's where the green kind of matches, or maybe it's over here. That's where he sees the horizon. And where the red guy sees the horizon is right here, right? So if I zoom in, you can tell I'm going to put a straight line from the red guy's horizon, and the green guy's horizon is lower than the red guy's. Do you see? It's pretty straightforward. Anyway, let's move on to the second easy proof for the flat Earth. Ta-da! Crepuscular sun rays. Pretty straightforward. What we have is, in the flat Earth model, the sun is local. And so as it moves across the sky, the light rays coming from the sun diverge because the sun is so close. This is a perfect image explaining it. If the sun is close, you got these holes cut out in this cardboard piece here. Light from over here will cut through the clouds in this direction. Light from over here will cut through the clouds in this direction. So you'll have crepuscular sun rays. If the sun is far away, like in this example, you got clouds, you're using the real sun to shine down on this piece of cardboard, right? And the light goes through, it lines up, and all the sun rays on a globe Earth should be straight. That's this argument. It's pretty easy. If you look at the way light comes through the cloud, just trace the light back to its source, and the sun is right here. You know, don't get confused. We're not, flat earthers aren't trying to say that it's a few miles above the clouds. It's up there. It's several, I would say maybe a couple thousand miles up off the Earth's surface, but it's not 93 million miles away, because if it was, all of the sun rays would be hitting the Earth at 90 degrees, as this image demonstrates. All right, let's move on to the final and one of the most simple flat Earth arguments. All right, take a look. This is one of the easiest ways to prove that the Earth is flat. If water is flat, then Earth is flat. It's that simple. According to the globe model, water curves and is sucked by gravity into the shape of a ball all around the Earth, right? What we see in reality is the light of the sun or the moon creating this pillar, this beam of light reflecting toward our eyes off of the water's surface. And so how that works, simply, is that the light from the sun is hitting water over here, and that's bouncing straight toward you into your eyes. All of the light coming directly to you is bouncing along this flat surface and causing this beam of light, this pillar of light, to reach your eyes, and your brain logically tells you this is a flat surface. This is what a flat surface looks like as light bounces off of it. You can do simple experiments. Take your dining room table, put a light on the other end, shine it toward you, and go get to the other side of the table and put your face right down so that you're looking along the table, and the light will do the same thing. It bounces along the table and creates this beam effect, this pillar effect, right? And that is because it's a flat surface. Now what you can do is, and notice this is a fisheye lens. You got the curve here seen from 20 feet above the water, which shouldn't be possible even on the globe Earth, so don't even bring that one up. Alright, so what we got here is a really big beach ball. I tried googling biggest ball on Earth. I wouldn't recommend it. Some pretty weird stuff comes up. What we're going to do is just pay attention to the way light acts on a spherical surface. Now, okay, this isn't a perfect sphere. I get that. But according to Neil deGrasse Tyson, Earth isn't a perfect sphere either. I mean, but you look at all the images of NASA, that NASA puts of the Earth, and you got pretty much a perfect sphere. I don't know what they're talking about with the pear shape, but water should be curving, the same way all around. And don't be confused, the size doesn't matter. A sphere is a sphere is a sphere, whether it's the size of a ball bearing, or if it's the size of the Earth, or if it's the size of the sun according to the globe model. Light would hit the surface of a sphere and act the same way because the curvature of a sphere is always the same. And I can argue proof for that because pi is always the same. You can use the same formula to discover the circumference, etc. of a sphere. You can do all of the formulas using pi because all spheres are the same, all circles are the same, and spheres are just three-dimensional circles. Take a look at the way the sunlight hits the sphere, all right? Even if you, and I've tried this, if you get your face right up close to the sphere and you take a little flashlight or whatever and you shine it at the sphere, you will never, ever get something like this. And this effect that you see is only possible on a flat surface. It doesn't matter how big the Earth is and how small we are. If you shrink down to the size of a person to scale on, if this were the Earth, the light that you see bouncing off of, from the sun, bouncing off of the surface here, it'll never, ever do this. Never. And that proves that the water is flat. There's no curve happening. If there was a curve over this length, this distance of water, and you can even, this is still true if you go up into an airplane and you see the sun on the ocean or the moon on the ocean, you'll see this pillar of light. It means that the water's flat. And you're only able to see so far because of perspective, because of the nature of the horizon on a flat Earth. Keep in mind what I said about all this stuff. We know that the Earth is flat by the way we can tell. Our brains tell us by looking at it. Simple scientific observations tell us it's flat. Anyway, thanks for watching. I hope that you learned something. If you are trying to prove to somebody that the Earth is flat, these are the three most simple arguments. Crepuscular sun rays, light on water, sunlight or moonlight on water, and whatever you want to call this one, seeing farther from higher. You can see farther from higher without having to look down, which means that you're looking across a flat surface. Alright, thanks for watching. I'll see you next time.